There comes a time in every man's life where he must realize that he has to man up and become a real man. However, in the course of being a real man, there come challenges. And in the course of overcoming such challenges, and the challenges keep mounting up, and they become harder and harder, they become more complex, pun intended, as he progresses being a real man. However, there comes a time when the real man snaps, and he realizes that being a real man just isn't enough. It is at that moment, in similar fashion to the way Goku first transformed into a Super Saiyan, and woo, yeah, still get goosebumps every time I think about that scene. It is in that similar fashion that the real man ascends his state to become a complex man. So anyway, we're going to evaluate these two badass looking integrals using contour integration. And we're going to need a couple of tools over here. First one being Cauchy, I think it's pronounced Cauchy, yeah, Cauchy's residue theorem. And this theorem states that the integral of some complex valued function f of z over a closed contour c equals 2 pi I times the sum of the residues of the function enclosed by that contour. And the other one is Jordan's lemma, which I won't state explicitly right now, but I'll tell you how to use it later so that you don't just get the feeling that I'm going to state it and then just say that, okay, by Jordan's lemma. No, I'm going to actually show you how to apply it so that it really, so that you can really absorb the mechanism and the working, etc., etc. And I'll do a separate video on proving Jordan's lemma later. But right now, I'm going to tell you how to use it. And we're going to evaluate both these integrals by considering just one of them, this one here. So consider I being the integral over the closed contour C of the square of the natural log of z, which I prefer to write in this manner. So it's the square of the natural log of z divided by z squared plus 1 dz. And now what exactly is our contour? Now, this is the complex plane, right? Where the x-axis represents the real part of the complex number and the y-axis represents the imaginary part of the complex number, right? And this is the origin. So let's define our contour to be a semicircle of radius r. So negative r here and r here. But there's one more thing to consider. The function that you're integrating over the contour is the square of the natural log of z divided by z squared plus 1. So we can't allow z to be equal to 0, otherwise the natural log will blow up. So we're going to have to circumvent the origin here. So in traversing our contour in the anti-clockwise sense, and once you get to the real axis, let's circumvent this origin here by introducing this smaller semicircle of radius, let's say epsilon, okay? And here you go. That's our contour that we're going to call C. I'm going to call this outer curve capital gamma and this inner curve small gamma. Now that we have this awesome looking contour, we can now write the integral over the contour C of the square of the natural log of z divided by z squared plus 1 as the sum of the following integrals. Well, you have the integral of this function over the curve gamma plus the integral of the function over the curve small gamma plus two integrals on the real axis. One is an integral from negative r to negative epsilon. And because you're on the real axis, you can just replace z by x, the square of the natural log of x divided by x squared plus 1, plus another integral, this time from positive epsilon to positive r of the square of the natural log of x divided by x squared plus 1. And we can evaluate the integral on the left-hand side using the residue theorem. So where exactly are the singularities of our function f of z? Well, the singularities, or the points where the function blows up, are z squared plus 1 equal to 0, which implies that z equals positive or negative I. Now, if you look at your contour, it's in the upper half of the complex plane, so you can't have negative I. But this contour can enclose positive I, which is just up here. It's 1 on the imaginary axis, right? So yeah, that's the only residue that we're going to need. So that means this integral that we called I, right? So that means I equals 2 pi I times the sum of the residues enclosed. So the residue, the only residue we're concerned here is the residue at z equals I, correct? And how do we figure out this residue? Well, this, in fact, it's a simple pole. It's just a single pole. So we have the limit as z approaches I of z minus I times f of z. That's how you evaluate the residue. Now, this is 2 pi I times the limit as z approaches I of z minus I times the square of the natural log of z divided by z squared plus 1 can be factorized in the complex world to z plus I times z minus I, correct? So these two terms cancel out, and you're left now, after evaluating the limit, with 2 pi I times the square of the natural log of I divided by I plus I is 2I, right? So the i's and the 2's cancel out, and you're left with pi times the square of the natural log of I divided by divided by nothing, in fact. So what is this term anyway? Well, the square of the natural log of I can be written as the square of the natural log of, now I is in fact e to the I pi by 2, correct? So this can be written, because the natural log and the exponential functions cancel out, you have I pi by 2 squared. So you have I squared pi squared by 4, and I square is just negative 1. So let's write a negative sign here. That means your integral, the integral I, is now equal to pi times this term here. So it's negative pi cubed by 4. That's what the left-hand side of this equation means. So let's replace this integral by the answer we got, which was negative pi cubed by 4. Now I'm going to deal with these two real integrals first, and then we'll deal with the integrals over the contours gamma and small gamma later using Jordan's lemma. And of these two real integrals, I'm going to consider this one first. For this integral, we're going to consider a change of variable like x being equal to negative t. Or you can just consider this as a transformation from the x world to the negative x world, because these are just dummy variables anyway, so you can perform the substitution or just consider this transformation. You'll get exactly the same results. So under this transformation, dx goes to negative dx, and the limits of integration are just, the signs are just flipped because of an extra negative sign. So you're integrating from r to epsilon the square of the natural log of negative x divided by x squared plus 1 times negative dx. Now, here's a negative sign here, and if you switch up the limits of integration, you'll get rid of this negative sign because of another negative sign popping up, right? So you have the integral from epsilon to r of the square of the natural log of negative x divided by x squared plus 1. Now, I think the coolest thing in complex analysis, or one of the coolest things anyway, is the fact that negative numbers have natural logarithms, or logarithms anyway. So what is the natural log of negative x, and then we can square it? Well, this can be written as the natural log of negative 1 times x, right? And it's just a cross written twice, so you get the idea. It's the natural log of negative 1 plus the natural log of x, right? And what's the natural log of negative 1? Well, negative 1 can be written as e to the I pi. And you can remember this using Euler's identity, of course, that this equals the cosine of pi plus I times the sine of pi. And the sine of pi is 0, and the cosine of pi is just negative 1. So e to the I pi equals, and anyway, this is Euler's identity anyway, the most beautiful, according to some, it's the most beautiful relation in mathematics. So this implies that negative 1 equals e to the I pi. And yes, it is absolutely gorgeous. So this is the natural log of e to the I pi plus the natural log of x. And you can take this out, cancellation. You have I times pi plus the natural log of x, and this equals the natural log of negative x. So let's use all of this information up here and write this now as the square of the natural log of x plus I times pi. And you can expand the square as, then you'll get the integral from epsilon to r of the square of the natural log of x plus I squared pi squared, which is of course negative pi squared, plus 2 I pi natural log of x, correct? And all of this is being divided by x squared plus 1. And this is actually pretty cool, because if you separate the terms out, then you get the integral from epsilon to r of the square of the natural log of x divided by x squared plus 1 minus pi squared, integral from epsilon to r again, 1 by x squared plus 1, which is awfully familiar, then 2 I pi integral from epsilon to r natural log of x divided by x squared plus 1, and I have no room for the dx, so you guys just get the idea. You get the idea anyway. So this integral is very similar to what we're after, and this is the other integral I wrote out at the start of the video. Okay, there is a lot of stuff going on, and I've rewritten the equation we had earlier, from which I just picked this integral that we can now replace. So I'm just gonna move this to the left here, and I'm just gonna copy and paste all of this. Okay, copy and paste. Gonna have to zoom out a bit here as well. Almost. Yeah, cool. And let me get rid of this tick mark. Oh, laser precision, I would say. And you have a plus sign here, and these two are exactly the same things, right? So just add them up. And some more maneuvering. I did not have to. Well, I had to anyway, you know, do that zooming stuff. And now I can add that dx that I didn't have room for in the beginning. So this is the equation we have so far. Now finally we're going to deal with these two integrals. And before we deal with them, let's remember what we were after. We were interested in integrals of this kind and this kind, where the lower limit was 0 and the upper limit was positive infinity, right? So we're basically interested in the cases where r goes to infinity and epsilon approaches 0. So that's the case that we're studying. Now, under these conditions, we want to study the behavior of these two integrals, which is quite trivial, so it is left as an exercise. Just kidding. No, that was just a joke. Relax. I am actually going to explain the application of Jordan's lemma here to allow these two integrals to actually disappear. Let me show you that they actually disappear rather than just saying that they disappear. Okay, so first up, let's consider the integral over the contour gamma. So this integral, much better. So this integral equals the integral over gamma of the square of the natural log of z divided by z squared plus 1 dz. And we remember what this was, right? This contour here was that big semicircle of radius r, right? So any complex number written as a vector on this semicircle can be written in this form. R times e to the I phi in the polar form, of course, where phi, of course, varies from 0 here to pi radians here, from 0 to pi. So this is the form of all complex numbers on this contour. So that means we can replace all the z's here by the polar representation. So if z equals r times e to the I phi, this implies that dz equals r as a constant, so is I, so I times r times e to the I phi d phi. And the limits of integration, as we see, are 0 to phi, correct? And we have the square of the natural log of r times e to the I phi divided by r squared e to the 2I phi plus 1 times, let me erase all of this to give myself some writing space, the differential element, which became I times r times e to the I phi times d phi. Okay, this does look awesome, but what do we exactly do with it? Well, for that, let's call it I1 and consider the absolute value of I1. So the absolute value of the integral from 0 to pi of the square of the natural log of r times e to the I phi divided by r squared e to the 2I phi plus 1 I r e to the I phi d phi. That's a lot of things to say. So we know that the absolute value of an integral over some contour is less than or equal to the integral over the same contour of the absolute value of the function. So we know this and we can apply it up here. So if I just take this absolute value, this modulus, inside the integration operation, I will have an inequality, a less than or equal to inequality. So here inside I have the absolute value of all of this stuff that I'm just writing and no longer saying. And yeah, I hope I just don't miss anything. Plus 1 down here, I r e to I phi d. Oh, forgot the yeah, I was about to forget something again. So yeah, and a d phi outside here or inside. Let me just rearrange this or shift it somewhere. Yeah, much better, because I want this to be completely visible. So yeah, d phi. That's a horrible phi. That's a horrible phi. Terribly sorry for that. Okay, d phi outside. Okay, and now what? Well, time to study the nature of this integral in the limit as r goes to infinity. And I think it's quite clear to you already that what the behavior of this integral would be. If I write this as the integral from 0 to pi of the square of the natural log of r times e to the I phi, divided by, if I take this r squared term as a constant if I factor out this r squared term, e to the I phi, it is a constant anyway with respect to integration. I meant to say if I just factor it out, and you can apply the absolute values individually, right? If you have two complex numbers being multiplied, z1 and z2, you can, the modulus of their product is equal to the product of their moduli. So yeah, that's pretty convenient. So I'm separating the moduli. I'm introducing them individually for this term and all of this here. And the modulus of this complex number is actually pretty neat. It's actually pretty neat. And again, I ran out of space there, so d phi. Anyway, so what is this? What is this term? We have I r e to the I phi modulus, which again can be written separately. E to the I phi. Now, the magnitude of the vector representing this complex number is 1, obviously. It's the imaginary unit. And r is a positive number, so 1 times r is just r. And e to the I phi has a very cool magnitude. It's the square of the cosine of phi plus the square of the sine of phi with the square root, which is 1, of course. So all of this just evaluates to r. So let's replace all of this and write it as r. And r cancels out with the r over here. And you're beginning to see some more light here. So yeah, this is extremely cool. So integral from 0 to pi, absolute value. You can separate some stuff here, natural log of r plus I times phi squared up in the numerator, correct? And divided by 1r left here, e to the I phi plus 1 by r squared d phi. Now in the limit as r goes to infinity, this term is going to go to 0, and we have a natural log term and a polynomial competing for supremacy upstairs and downstairs. And we actually have two. Even if we expand the square, we'll have the natural log of r squared plus minus phi squared, that is minus phi squared plus 2 times I times phi times the natural log of r. So we have two logarithmatic terms competing with a polynomial down here. And we know that polynomials go to 0 polynomials grow much faster. Polynomials grow much faster than logarithms. So the net effect you're going to get is that all of this, this entire structure, all of this complicated stuff that I'm tired of speaking out loud, all of this is going to go to 0, and the integral collapses to 0, which is awesome, by the way. This is absolutely awesome. I mean, it was kind of annoying to run out of space, but it was totally worth it. So this integral here, the gamma integral, where to go? Yeah, it goes to 0, and in the limit as e goes to 0, the integral over the smaller semicircle is also going to go to 0. That is left as an exercise to you, the watcher, because it's very, very simple to prove. It is very trivial, and I'm not saying that as a math teacher. I mean, literally, in this case, literally, it is very trivial to show. So even if you don't get it, you can ask me in the comments below. So anyway, these two integrals vanish beautifully, and you're left with a very, very cool and easy to solve equation. So let me just give myself some space, some more writing space here. Yeah, that's much better. So anyway, we're left with this integral here as well. So in the limit, we're considering the limits as e goes to 0 and r goes to infinity, right? So let's replace all the e's, all the epsilons. I think I called that e. Very sorry, terribly sorry for that. That is a horrible thing to call. That is a horrible way to address the epsilon. So really sorry about that. So 0 to infinity, and in the limit as r goes to infinity, in the limit as r goes to infinity and epsilon goes to 0, this is a constant, right? It's not going to be affected, which is, again, really convenient. So we have negative pi cubed by 4 here, equaling to twice this integral, and we all know what this evaluates to, right? This is going to be, I'm just going to call this I1, okay? And I'm going to call this I2, so plus 2 pi I2. And this here is going to be negative sign out here, pi cube by 2. And we can add this to both sides, correct? So in case we decide to do that, we have a pi cubed by 2 minus pi cubed by 4, which is of course pi cubed by 4 anyway. And we can also divide both sides by 2. So this implies that I1 plus pi times I2 equals pi cubed by 8. Now, as promised, we were going to solve both integrals. Now, pay close attention to the left-hand side of this equation I've written. The left-hand side is basically an imaginary number, right? There's a real part and an imaginary part. And this equals a real number. A real number is just a complex number with the imaginary part being equal to 0. So if we equate the real and imaginary parts, we get the integral from 0 to infinity of the square of the natural log of x divided by x squared plus 1 dx equal to pi cubed by 8, and the integral from 0 to infinity of the natural log of x divided by x squared plus 1 dx equal to 0. So yeah, that was awesome. Thank you very much for watching the video. Be sure to like and subscribe. Thank you. See you next time.